Work, work, work. It comes in many forms. Machines do it, people do it. We sometimes love it, sometimes hate it, but usually can't avoid it, because we all do some kind of work every day. Work is not even confined to machines and humans. Any animal that moves something from one place to another does work. But how do you measure work? What do you call work? Your definition of work may be quite different from that of a technician. For example, homework is not work. In fact, thinking, no matter how difficult, is not work in a technical sense. Why? Because thinking only changes your mind. For a technician, work is done when force causes a change in the system. So controlling work is controlling what the force does.
The 4200 model Prab robot's a relatively simple robot. You'll find a lot more sophisticated machinery on the market, but this is easy to maintain, it's cost efficient, and it's strong. It's durable. It operates at about approximately 700 pounds per square inch of hydraulic pressure. It's not a very smart robot. When the control drum tells it to do something, it continues doing it until it literally hits something and to make it stop. And that's how we control the actions, vertical and horizontal, for a Prab robot. We actually run it into a stop, a mechanical stop. And by varying and by adjusting these stops, we can get surprisingly accurate.
The robots do work in two ways. First, they use force to move the parts a distance. Then they use torque to rotate through an angle. When Bob Lala adjusts the stops, he's controlling a very powerful force and how that force acts over a distance. Using force or torque to move something a distance is work in a mechanical system. Work in a fluid system is done when pressure moves a volume of liquid or gas. And in an electrical system, voltage does work moving an electric charge. In each case, force or something that acts like force causes some kind of change or movement. To measure the amount of work, simply multiply the force by the change. So for things like homework, the only work being done in a technical sense is when that thinking causes your muscles to move something from one place to another. So, is work being done in these cases? Not technically, because nothing changed or moved. Voltage, force, pressure, and torque alone are not enough. Now work is being done. Work is only done when something changes. That is, when something moves, turns, flows, or changes shape. Another important thing about work is the fact that time is not part of the formula, only force and distance. So that means that this tractor does the same amount of work moving the aircraft a distance as the aircraft itself does when it rolls the same distance under its own power. The jet engines do the work a lot faster, but the amount of work is still the same. The same is true of these two people. As long as they have the same weight, believe it or not, they're both doing the same amount of work because they both raise their bodies the same height. Work. It only happens when force or something that acts like force causes something to move, turn, flow, or change shape. And if you feel that you're working too hard, try getting some help. From Gravity. What does working out really mean? Work is done on something when a force causes that something to move. So muscles do work moving bodies or weights certain distances. The heavier the weight, or the greater the distance it travels, the more work is done. To do work in a mechanical system, two things are needed. One is force. The other is movement while that force is applied. The movement is the distance. So to measure the amount of work being done, say, by a machine, you multiply the force it exerts by the distance the object moves. If there's force, but nothing moves over a distance while that force is applied, no work is done. Watch this scene and see if you can tell when work is being done. What you've just seen is work being done in a mechanical system. When the barbell was lifted, force was applied in an upward direction, but work was not being done the whole time. To do work, you need both force and distance over which the object moved. So work was only done when the barbell was moving, not when it stopped at his chest and over his head. Now watch the robot. The same thing is true for machines. Work is only done when the object is moved by force. You need both to do work. When the robot stops moving, it's not working, even though it still exerts force. No matter how long an object is held in the air, no matter how much force is exerted, no mechanical work is done until that object moves a distance.
Okay, hold it a while. Just hold it a while. Hold it. Okay, get it down.
Of course, you try telling the weightlifter that. The definition of work as force times distance is easier to remember if you think of the units of work, the foot-pound or the Newton-meter. Pounds and newtons are units of force. While feet and meters are units of distance. So force times distance is work. For example, to find the work done by the winch lifting this elevator, multiply the pounds of force needed to lift it by the number of feet it travels when that force is applied. Feet times pounds is foot-pounds of work. Measuring the force in newtons and the distance in meters does the same thing in metric. Notice that time is not part of this formula. So the work done on the elevator, lifting it from the ground to the top of the building, is the same whether it's done in one move or whether it stops at every floor, represented by these dots. The only time the amount of work changes is if the weight changes, when people get on and off, because then more force is needed to move it. We constantly hear about efficiency, but what does that mean in a technical sense? Efficiency is a comparison of what we get out of a machine over what we put into it to make it run. The difference between the amount of work put into a system and the amount of work you get out tells you how much work is being wasted in the system itself. In this case, the person is pulling on a line, exerting a force, and moving it over a distance, so work is being done. At the same time, the pulley system does work on the drum. But the distance the drum moves is shorter, so does that mean the amount of work is less? No, because the hands exert a smaller force over a long distance, while the pulley exerts a greater force over a shorter distance, so the amount of work is the same. Well, almost the same. If the work in equaled the work out, the machine would be 100% efficient. In reality, no machine has ever been invented that's perfectly efficient. But it's important to measure efficiency because it tells you how much work is being lost in the system. So far, we've only been talking about work being done to move objects in a straight line, but many mechanical systems move objects in a circle or rotate a shaft. The formula is basically the same, except that the force needed to rotate an object is torque, and the distance is measured in angles. In short form, that's T times theta. T for torque is the force. Theta, the angle, is the distance. Measuring theta, or the angular distance in a rotating system, can be done in two ways: degrees or radians. For example, the drive mechanism on this Ferris wheel creates torque to rotate the system. If we want to measure how far the Ferris wheel rotates in degrees, start with a radius. That's a line from the center out to the edge. When the wheel rotates, it moves through an angle. You find the angle by drawing a second radius at the final position. What you measure is the angle between these two lines. In this case, the angle is 57.3 degrees. So this wheel has just moved through 57.3 degrees of rotation. That's angular distance in degrees. The other way to measure angular distance is to use the radian. A radian is related to the radius because if you take a radius and wrap it around the outside of the wheel, then rotate the wheel through that angular distance, you form a radian. In other words, in a radian, this distance is the same as this distance. Whether you measure distance in radians, angles, feet, or meters, when you multiply that distance by the force needed to cover it, you're measuring how much work was done. Since machines were invented to do work for us, it's not only important to know how much work we want them to do, but also be able to measure exactly the amount of work they're capable of doing.
That's a wrap. Clean it up.
Whenever we move, most of the muscles in our body do work on the bones. The muscles apply force and move the bones a distance. This force moving an object over a distance is work in a mechanical system. But there's one very important muscle in your body, which is probably the hardest working of all, and it does not move a single bone. Your heart is an example of work being done in a fluid system. Every day, it uses pressure to move blood through your body. In your lifetime, it will pump up to 230 million liters of blood, enough to fill a large football stadium. Work in a fluid system is similar to work in a mechanical system because something is being moved from one place to another by force. But instead of measuring force, pressure difference acts like force to move fluids. And instead of measuring the distance the fluid moves, we measure how much fluid has moved, or the volume. So work in a fluid system, like moving milk in this dairy farm, is only done when a volume of fluid is moved from one place to another by pressure. If the fluid does not move, no work is being done, even if the pressure is present. There are two ways that work can be done in a fluid system. One is open, the other is closed. In an open system like this power dam, the pressure changes, but the volume remains constant. In a closed system like this pump, the pressure remains steady while the volume changes. Let's look at the first case. In some power dams, a portion of the water that flows through the dam is pumped back up at night. This gives them an extra reserve during the peak hours. The pump that moves the water from the base of the dam to the top does fluid work. To calculate that work, two things are needed. First, the volume of water. This can be read directly from the flow meter. Next, we need to know the pressure difference. You'll recall from our study of force that pressure in a fluid can be calculated from the depth of the water. This gives us delta P, the pressure difference between the top of the dam and the bottom. Remember that delta means difference. So the work done by the pump in the dam is the pressure difference times the volume. This is work in an open fluid system. Now let's look at an individual part of a pump, such as the piston in a piston-type pump. In this case, the pressure exerted by the piston does not change. But when the piston moves the fluid into or out of the cylinder, the volume changes. This volume of fluid that was moved is delta V. So the work done by the piston in the pump is pressure times the volume difference, or delta V. This is work in a closed fluid system. By the way, delta V is also referred to as the displacement of a cylinder, and it's one of the big selling points in engines. So if you see 350 cubic inches, that's the delta V, the displacement of all the cylinders. In other words, it's the volume of gas that is moved through the cylinders by the pressure from the pistons. A jet engine is a good example of work being done in an open fluid system. When air enters the engine, it's compressed, mixed with fuel, then ignited here. When the burning gases expand, they create a large pressure difference. This causes work to be done on the gases, forcing them to move from the area of high pressure to low. As they move, they pass over the turbines, causing them to spin. They in turn spin the intake fan that actually provides the thrust. To Jim Hawkins, this fan does fluid work.
Before, we saw fluids doing work on the mechanical system. So we look at the fan, we see an example of the mechanical device doing work on the fluid system. Now, some engines have large intakes such as this, and some use small fans, as this is an example. Now, the relationship between volume of air and pressure is such that if we reduce the volume, we have to significantly increase the pressure in order to maintain the same amount of work. Now, when we do this, we have to significantly increase the speed. This causes an increase in noise. Therefore, the trend in aviation today is to use a large intake moving a small or large volume of air at a reduced speed.
You can hear this effect for yourself the next time you're at an airport. Listen to the sound of jets with large fans compared to those with small ones. Engines with large intake fans move large volumes of air under low pressure. This is why some of the biggest jets in the world make the least noise. Military jets, on the other hand, have small intakes and use extremely high pressures, making them the noisiest of all. But whether noisy or quiet, the amount of work done by the engine depends on both the pressure, which acts like force, and the volume of fluid that was moved. Work in fluid systems completely surround us every day. When you watch a weather forecast, the weather person is showing you the delta P's for the Earth. It's these pressure differences that cause the massive volume of air that surrounds the Earth to move from one place to another. With no work done on the air, there would be no wind. Work in a fluid system is useful because it can be recovered and turned into other kinds of work. For example, the work done by the sun to move the air around the Earth and generate wind can be converted into mechanical work of turning a windmill. This mechanical work can then become electricity. In the same way, the work of raising water the height of the dam can be recovered when the water flows back down and passes through a turbine. But remember, like work in mechanical systems, pressure is not enough. Work is not done until the fluid moves. Every day we are completely surrounded by electricity doing work. In fact, electrical systems have probably invaded more aspects of our lives than any other system. Although we see many devices every day that use electricity, they are not direct examples of electrical work. We don't actually see electrical work, we can only see its effect. It's just like these giant windmills. You cannot see the wind, but you can see the effect of the wind, when that fluid work is turned into the mechanical work of rotating the blades. That mechanical work is then turned into electrical voltage, which does work moving electric charge through the wires. So the lights that are over your head right now, this television that you're watching, and any device that you plug in or run on batteries all operate as a result of electrical work that's being done. The motors in this trolley bus do mechanical work because they use force to move the bus over a distance. Electrical work is done when voltage moves the charge from the overhead wires along these arms into the circuits of the bus. Like fluid systems, instead of measuring how far, we measure how much charge has moved. So electrical work is voltage times the charge. In short form, that's V times Q. For Ralph Burton, moving electric charge determines how well his robot performs.
This is an electrical operated robot that does seam welding. Electrical movement or movement of the charges are being done all the time in this type of a robot. There is an electrical charge moving down this line right to this wire that would determine the weld of the robot.
This is all that electrical work is, the movement of charge from one place to another. The sparks, the heat, the movement of the motors are all effects of electrical work, not the work itself. Electrical work is moving electrons, incredibly tiny particles that make up the outer part of the atoms within the wire itself. Electricity is invisible. Still, we're able to move electricity across the country. So it's important that we know how to measure the amount of electricity on hand and the amount of work it can do for us.
Okay, hold it. We need to pause here for a little demonstration. You just saw some animation that showed electrons going through a wire, and it made electrons or electricity look like little ball bearings. Well, there's two things that need to be said here. First of all, electrons are incredibly small. They're too small to be seen, they're totally invisible, and in fact, they're so small, they can't even be measured. But that's good, because when we move electrons and make electricity, we move a lot of them. Now, the unit of charge is called a coulomb. Now, a coulomb is a million electrons. Well, how many is that? Okay, if I reach down, I can pick up maybe 500,000 grains of sand in my hand. So try to imagine a million grains of sand. How much would that be? I'll give you a hint. This is about a million grains of sand. Now think about a battery. When a battery is charged, it can be charged to 8,000 coulombs. So that means 8,000 times a million. That's an awful lot of electrons that are stuffed into this little battery that move from one pole to the other. How many grains of sand would that be? Well, that's more than all the sand that you can see on this desert. In fact, it's enough sand to cover the entire Earth.
Moving that many electrons is what I call electrical work. You can appreciate how tedious it would be to count that many electrons. So there's no such thing as a Coulomb meter. Instead, the amount of electrical charge is measured in amperes or amps. 1 amp is 1 Coulomb moving past a point in 1 second. Think of an ampere as counting how many dump trucks pass by instead of counting the grains of sand in each truck. So the amperage of a battery is the amount of coulombs it can deliver every second. Or in other words, how much electrical work the battery can do. The voltage is what acts like force to move that charge out of the battery, through the circuit, and do the work. Like other forms of work, it doesn't matter how fast or slow the electrical work is done. The amount of work is still the same. This is what Lee Klaus has to deal with every day when he drives to work in his extremely quiet car.
I have one of the cleanest and most efficient cars in town. It's an electric. It has 8 batteries in front and 8 batteries in back to give me a total of 16 6-volt batteries. Give me a 96-volt power pack to operate the electric motor, to give me my power. This power pack is a very efficient power pack up to a point, but I am limited in my range, so I have to be aware of how far I'm going and allow myself enough power to get back home when I get there. In a gasoline car, you have to be concerned with the amount of gas you have. In an electric car, you have to be aware of the amount of charge in the battery pack and use that charge to get the most efficient amount of work out of the car. One thing you don't want to do is race away from stop signs or try to show off for somebody who wants to drag with you, because this uses energy much faster and it reduces the amount of range you have. So I prefer to start off slow from the stop signs and drive at a reasonable speed, save the energy in my battery pack so that I can get some more extra work out of them to run my air conditioner.
The work being done by the batteries to drive this car is not all being converted into mechanical work of moving it forward. Some of it's lost as heat, which is generated by the motors. To find out how much work is wasted, or in other words, to measure the efficiency of this car, we can compare the amount of electrical work going into the system and the amount of mechanical work that comes out to move the car. Fortunately, the unit of electrical work, the joule, is exactly equal to the unit of work in a mechanical system, the Newton meter. So if you find how many joules of work the battery is doing, which is voltage times charge, and compare that to the number of Newton meters of work the motors are doing, you get the efficiency. If the joules and Newton meters are the same, the system is 100% efficient. Well, no machine is 100%, but by comparing joules and Newton meters, you can find how much work is lost. Electricity is a valuable and expensive form of energy, so we need to use it as efficiently as possible. We pay for the amount of electrical work that's done moving charge through our homes. And like other forms of work, voltage alone is not enough. There's usually voltage in a household circuit, but electrical work is not done until the current actually flows. Everyone has their own definition of work, but to a technician, work is an efficient use of force that causes some kind of change in a system. We have seen that the definition of work for a machine can be quite different than that for a human. A machine is at work only when it's moving. Whereas people are at work all day long. Work in a technical sense is done only when a change is happening, when something is moving or changing shape. Two things are needed to do work: force, or something that acts like force, and the amount of change, such as the distance. People, on the other hand, feel like they're working as long as they're exerting force, whether it causes a change or not.
Just hold it a while. Hold it. Okay, let her down.
But force alone is not enough to do work. So even if voltage, force, pressure, or torque are present, they do not do work unless they cause a change. That change could be the flow of electric charge caused by the voltage, the movement of an object caused by force, the flow of a volume of fluid by pressure, or the spin of an object caused by torque. No matter how powerful they are, if there's no change, there's no work. Work is not just a measure of force, it's a measure of exactly what force does. Work is done when force causes an object to move. Work is done when torque causes an object to rotate through an angle. Work is done when pressure moves a fluid. And work is done when voltage moves a charge through a circuit. Whether that change happens quickly or slowly doesn't matter, because the same amount of work is done if the force and the distance are the same. When there's a job to do, we need to know two things. How much work will it take, and what machine can do that amount of work. We can then match machine to the job most effectively. This is what a mechanic does when selecting the right tool for the job. Robots, for example, come in a variety of sizes and types, and are capable of doing many different kinds of work. But robots are expensive machines, so the decision whether or not to use a robot is based on measuring work. The amount of work that needs to be done is compared to the amount of work a robot can do. If a robot is too small for a job, it will not be able to do the work required. Likewise, if it's too large for the job, it will not be working to capacity. This is called job efficiency, comparing work. And if a machine doesn't do a job efficiently, it can always be replaced by a human. Comparing work is easy to do because the units of work can be converted. For example, a foot-pound can be converted to a Newton-meter, so the work in a mechanical system can be compared to the work in a fluid system. Likewise, the electrical unit of work, the joule, is exactly equal to the Newton-meter. So even though moving an electric charge is very different from moving a solid object, the amount of work in the two systems can be compared. For example, robots have three different kinds of work taking place at the same time. Electrical work runs the hydraulic pumps. They create pressure and do fluid work moving the pistons, which then do mechanical work moving the objects. By comparing the electrical work in to the mechanical work out, we see how efficient the machine is. Robots tend to be fairly good. A car, on the other hand, is rather inefficient. Pressures in the engine do fluid work on the gases, which then becomes torque and does mechanical work turning the wheels. But when we compare them, the wheels are only doing about half as much work as the engine. The rest was lost as heat. Machines are nothing but oversized tools. Measuring work not only shows us what force can do, it helps us choose the right tool for the job.
Work, 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 work.
This program was produced at the facilities of Telemation Productions and is part of Principles of Technology, a project of state and provincial vocational and technical education agencies in association with the Agency for Instructional Technology and the Center for Occupational Research and Development. Together, serving education.